Welcome to part 3 of the statistics overview series, in which we would finally get to talk about statistics, specifically inferential statistics. How do you calculate quantities based on a sample of data and make conclusions about the whole population? Specifically, we'll talk about two general areas: making estimation, so some unknown parameter will make it estimates about it, and hypothesis testing, which is about decisions, making decisions. You say you create two alternatives and then look at the data and say we can reject this, or there's not enough evidence to reject this theory. So there's a lot of technical jargon. We'll get to that in a later. As is usual, the first thing to do is clear all outputs. Oops, that jumped a lot. And this is the notebook where we're working, 03 stats. If you have it on your file, this is the one you should be opening. Here is the outline. Okay. You can ignore this cell. It's just importing a bunch of the libraries. We don't want to discuss it. Okay. In this notebook, we finally going to answer the two questions. Remember Amy's from the previous videos. The scenario we were working with is Amy, who has employee lifetime value data for the two groups: employees who took statistics course, employees who didn't take statistics. So we want to know, is there, first of all, we want to know, is there a difference? So did the statistics training do something for them? Are they better employees? And the second question, so assuming the first one is yes, is how much, what is that difference? Is it a little bit? Are they 10 points, EOV points better? Are they 100 points? Are they? So the two, these two questions correspond to the hypothesis testing and to the estimation aspects we'll be discussing. And we finally have the tools to do that. Before we talk about these, so I had a lot of trouble when I was learning statistics. I had the trouble to say, well, there's all kinds of formulas and procedures to follow. And only when I understood what estimators are did everything become clear. Because there's some math, and if you understand the math of estimators, hypothesis testing and estimation become much easier to understand. You don't need to memorize the formulas, you understand them as special cases of the general equation. Okay, so an estimator is a function computed from data, from a sample. And when you think about it, it's an application of probability theory, just to know what is the variability of this estimator. So when you compute it on a particular sample, you have a number, I have a value. But using probability theory, you can think about the estimator for hypothetical distributions, and what are the properties of this estimator for random samples. So that's called the sampling distribution. So thanks to your understanding of probability theory, we can actually do the details with real math, not like giving you simplified formulas or something. Okay, and why do we do this? Because hypothesis testing and estimation are both uses of estimators. Here we're going to use estimators to estimate, surprise, surprise, and not just get a number, but able to obtain the variability of our estimates. So we'll have guarantees, like I predict this, but it can be between here and here. And in hypothesis testing, similarly, we'll estimate a parameter, but also include the errors around it, which will allow us to make decisions. So we'll see all of that, but let's start with the math of estimators. Okay. At this point, the video doesn't need to be this big. Okay. So when I say estimator, you just think about a function. The same functions you know from high school math. It's just a function computed from samples. So this is a sample of size n, and it gives you a number. There are all kinds of names we already know about estimators. We called statistics when we computed the mean, the standard deviation from a sample. But now I don't want you to think about the number, like what is the mean is, right, the average of the values in a sample. I want you to think of the function that computes the mean. So like that's why the statistic is, yeah. So the key thing to understand is the relation between this quantity, which is the value of the estimator for a particular sample, and this quantity, which is the value of the estimator computed on a random sample. So this is a number. You have some sample, you compute its average, you get one number. This is a distribution. So you actually take the set of all possible samples. So they're random. That's what a random sample means. You don't have one number, you have a distribution of samples. And on that, you compute the same estimator, so it's the same function, but now you get a distribution. So this tells you how that estimator behaves in the long term when you take multiple samples and the distribution. So because it talks about a distribution based on samples, the distribution for this quantity is called the sampling distribution. Okay, so this is a number, this is a random variable. And the properties of this number, so when you make an estimate, you want to know how good is that estimate. Is it accurate? Is it precise? Is it estimating the right quantity? Or is it off, like a biased estimator? And also when this is the thing you're estimating, are your estimates close to it, like a wide variability, or very tight, like it's like, whoa, my estimates are going to be really good. So all that information is in the sampling distribution. And because you know math, you'll see, you will learn how to compute the sampling distributions instead of taking some formula from someone. Okay, two examples that you're already familiar with, just to reinforce the concept. The sample mean, this is the formula, right? You add all the values, divide by the sample size. Let's call that computation here, the mean, let's call it the function g. So given a sample, add up the numbers, divide by n. And this estimator estimates the population mean. So if you want to, these samples, assume it comes from a population, and if you follow this, if you compute g of that sample, it gives you an estimate of the population mean. It's the best estimate you can get. Now imagine computing the same g over multiple samples, or a random sample. So imagine just continuously taking different samples of size n and computing the mean. Take a new sample, compute the mean. Take a new sample, compute the mean. So the distribution you will get is called the sampling distribution of g. And this will tell you how the sample means you compute, what is their variability. So again, the same function when computed on a sample, it's a value, it's an estimator. Estimate, it's an estimate and like a number. And the same function computed on a random sample tells you a distribution. Here's the second one, the sample variance. With lowercase s, it tells you the variance of a particular sample. Why do we like this estimator? Because it's an estimate of the population variance. And how does it vary? Like, is it a good estimator? Well, its distribution, its sampling distribution, is computed by analyzing the properties of the same function h on a random sample. Okay, I know I'm repeating myself, but this is a key thing. Now, we get to the main one. So these were examples. We're not going to discuss them further because they're too basic. The one we need, the estimator we need, and we already saw it, is the difference between group means. difference between group means. So imagine you have a group. So this is a sample, and this is another data sample. You compute the mean in each groups, and you subtract them. So this is what we have in the statistics. In the Amy's, in a data analysis scenario, we had the group of statistics, employees who received statistic training, and employees who didn't receive statistics. And we want to compare these two groups. So comparing the means, D, the difference between me, lowercase d, this is for a particular sample, is a good estimate for the difference between population means. And the variability is, the sampling distribution, we use the capital letter D, from hypothetical random samples from the two groups. That's the, yeah. So you see, it's each time it's the same concept. You have an estimator, which tries to estimate some quantity, and the variability, how does this vary around this quantity, is described by the sampling distribution. Okay, let's dig into this a little bit more, specifically this one. Okay, imagine two groups, right? And to make the model precise, right, because this works for any kind of distribution, but we want to have some formula. So let's assume the two groups are normally distributed. So group A has a mean mu A, group B has a mean mu B, and the variance here is sigma A, and the variance here is sigma B. So just two curves, BR and BR. Okay, take samples from each group, NA and NB, so it could be different size, could be the same size. Compute the mean in each group, and then subtract the difference. So, right, this is what the estimator tells us. We're interested to know in the difference between these two population means. We're going to estimate that by computing the sample difference between means. Okay. Here is a function that computes that, right? Compute the mean of sample 1, compute the mean of sample 2. Let's try that function for a population with these parameters, so mean 300, and let's assume we have samples of size 5 and 4. Okay, here is now a sample from that group, and here is a sample from the group B, and we compute the difference of means. Okay, the number we obtained, 96, is an estimate for the true difference between populations. In this case, we know that the true difference is 100, but the estimate we obtained from the samples is going to be different, right? Each time I run this code, I get a different sample, and we see a number. Our estimate computed from that sample varies, right? It's the true, it should be 100, but we get 97, a little bit over, a little bit less. So how can we characterize? So this is the first step. This is why we're doing statistics. It's not just getting one number and say, oh, well, that's my best guess by. We want to know the variability of our estimates. So what did we say? What tells us the variability is the sampling distribution. So since we know the model and we know everything about the estimator, we can actually obtain the sampling distribution directly. Okay, so let's do that together. The sampling distribution of D means what I just said. Capital X A is a sample of size NA, and capital XB is another sample. Now what does this do? This means it is not one sample, it's a random sample. It means it describes the scenario where I repeatedly take new and more samples over time. So it's, in theory, it would be infinite number of samples and the distribution infinite samples. But in practice, we're just going to do that with 1,000 samples, because 1,000 is big enough number for to see a curve, to see a distribution. Okay, so by definition, the sampling distribution, so this is the function that will give us that, of any stat function. So we're interested in the difference between means, but the function here works for any. It's exactly what we did here. We computed two samples and computed the sample. We computed the estimator, the function on these samples. But we're going to repeat it n times, in this case 1000. So what does it do? Repeat 1000 times, generate a sample from group B, compute the statistic, whatever this function is, compute it, and then record it. So this is as imagine running this cell hundreds of times and recording the values. What do we get? I'm just calling, so this defines the function, now I'm calling it, and we generated 1000 samples. Let's look at a few of the values. We saw that earlier. Now let's plot it. I did not run the cell. It looks like some sort of shape. Maybe normal, who knows? Okay, so the difference of means between group means for computed from 1000 samples. When we look at them, you see what happens. So this is what the sampling distribution means, is that on average it will be 100, but you see that they vary. Your estimates, the difference between means, estimates, have a natural variability around the correct answer, 100. So understanding the if you understand the properties of this distribution, we can do statistics, because then we can say every time we make an estimate, we will know how it varies, how good our estimates are. So this approach we used here with 1000 samples is called the simulation method. It's just directly computing 1000 samples. But it's one, and so half of statistics you can think of one of the tools we have is simulation. The other tool we have is math. So let's see what we can do with math for the same problem. So D means, right? This statistics, the difference between group means, we can use math to get a distribution for D. Let's see first it's a two-step process. The first step is to observe the sample mean of any distribution from XA is the average of the sample has the mean equal to the population mean, and this, remember, the central limit theorem tells you that the sample mean there's a square root of n in the standard deviation. So in the variance it's 1 over n. So we have this expression. We know the means are normally distributed with these variances. And when we subtract the two, we have this is a random variable, this minus this random variable. There's another rule of probability theory that says that the means get subtracted and the variances get added. So in other words, probability theory tells us that the distribution of the difference between group means has mean difference between the two group population means, and variance and standard deviation equal to square root of the sum of the variances divided by the sample sizes. But is this math any good? It seems to be pretty good. You see what happened? So this was, we obtained this distribution by literally simulating what the repeated samples, and then the model, the curve here, is obtained through math. Okay, so what does this mean? This means that we have an understanding of the estimator we need to know. Okay, well, let's tell you right away that all of this was preparing for Amy's statistical analysis. We have group S, group NS, and we want to know the math. We want to know a simulation. We want to know the math. How exactly is this going to vary? How the the variability of our estimate of the difference between group means, is it we want to be able to characterize that. So we just saw the simulation method and the math theoretical model for estimating that. And what we can do from here on is build models that are specifically adapted to our statistical analysis. So what do we know from the data chapter? We concluded with some measurement that we know that the difference between the group means is 130, and the standard deviation with group S was 233. Standard deviation with group NS is 265. So this is all we need. So that's what we have here, 265 to 233. So we can build now a model using what we just saw for the difference between group means, and using that model we can start to do hypothesis testing, we can start to do estimation. So in a way, what we analyzed here with group A and B is a general purpose template anytime we want to analyze two groups. In the next video, we're going to continue with a specific analysis for the groups Amy's statistical analysis, the comparison of the two groups. So see you in the next video.